We are ready for Chapter 5, Gases. We're going to start with 5.1, which discusses pressure. And pressure, as we will discuss it in this course, it's caused by gas molecules colliding with each other and with the walls of their container. Here are some different units, and you're going to copy these down. Oh my goodness, what just happened? That was not what was supposed to happen. There we go. So these are all the different units for pressure and how they are equivalent to one another. To measure pressure, we use a manometer or a barometer. These are examples of manometers. We have a gas in a container, and then there's an opening to the environment. Atmospheric pressure is pushing down. You might be able to see these arrows pointing down. And the gas is pushing this way. So if you look at this liquid here is mercury, and if I were to ask you, who's pushing harder, the gas or the outside pressure? Well, if you look here, do you see that this side is farther down than this side? That tells you that atmospheric pressure is pushing more or has a larger pressure than the inside pressure. So the gas would have the atmospheric pressure, whatever it is, minus the height from the top here to the top here. So this difference from here up to here would be H, and the gas pressure is the atmospheric pressure minus H, because the atmospheric is clearly larger since the mercury is lower on this side. Whereas on this side, the gas has a bigger pressure because the gas side is lower. So here, the gas pressure is your atmospheric pressure plus this distance from here to here. And if you're curious in seeing where that original picture came from, here's the website where it came from. All right, gas laws. Boyle, Charles, Avogadro. Boyle's law, pressure, volume. I think it's silly that we ask you to memorize these things, but you're asked to memorize that Boyle's law talks about pressure and volume, and this is Boyle's law. Right there. Charles' law, volume and temperature. There's Charles' law. Something weird happened with his ideal gas level. We'll fix that in a minute. Avogadro's law is volume and moles. It's a direct relationship. Notice this is a direct. If you look here, you'll notice the ones are on top, and here the twos are on top. It doesn't matter. It works either way. And then this one, here we go, the ideal gas law. Right here. If we combine all those laws we just looked at, we can get this relationship: pressure, volume equals moles times the universal gas constant times temperature in Kelvin. That's very important. Okay, we're not going to do any practice problems. I'm assuming you can do these, and you'll get some practice in class. We're going to move on to gas stoichiometry. We've already learned stoichiometry, and now we're just going to use this ideal gas law along with stoichiometry. Why is that? That's irritating me. I don't like that there. Okay, so we use the ideal gas law to calculate moles of a substance or volume of a gas, and then you use just regular old stoichiometry. There's some important things. At standard temperature, which is 273 Kelvin or 0 degrees Celsius, and standard pressure, which is 1 atmosphere. The volume of any gas is exactly, do you remember? 22.4 liters. And there's a nickname or a little acronym for this. It is STP, and that stands for standard temperature and pressure. So let's do a problem. Here's all the information about the problem. And we're going to convert mass of sulfuric acid to moles of ammonia, and then we will put those moles of ammonia into the ideal gas law along with its temperature and pressure to get the volume of ammonia needed. You can do this on your own. You shouldn't just copy this. You should remember how to do this. So convert mass of sulfuric acid to moles. Remember, there's the kilograms. Get that to grams. And then we need to go grams to moles, and then moles of sulfuric acid to moles of ammonia, and then plug that into PBR equals nRT. You should pause because I'm about to show you the solutions. There's your solution. Okay, new problem. Quicklime is produced by the thermal decomposition of calcium carbonate. This is quicklime right here. We want to calculate the volume of carbon dioxide at STP produced from the decomposition of calcium carbonate by this reaction. Now, we know the gas is at STP, so we can use that conversion factor that 1 mole of gas is 22.4 liters. We learned that right up here. 1 mole of gas is exactly 22.4 liters. We can make a conversion factor out of that. And this solution is just a stoichiometry direct conversion, just like this problem. And one of the steps will be 1 mole of CO2 is 22.4 liters. You pause this and do it yourself. And here's your solution. All right. Should make that red, huh? Red, 34.1 liters of CO2. All right. Now, you can find the molar mass of a gas from its density, and we use what's called dimensional analysis. It's a fancy word for analyzing units, because dimension is a unit. Your dimensions are your units. Analysis, analyze. So, we have two equations. Molar mass is mass over moles, and in the ideal gas law, moles is N. Density is mass over volume. In the ideal gas law, we write volume as V, and we know PV is nRT. If we isolate moles in this equation, right here, and we isolate V in this equation, we can obtain, I want you to go ahead and do that on your own. Isolate N in this equation, isolate V in that equation, and here's your solution. You should have paused. So we isolate N and V. Now we're going to substitute this N here into N, and this V here into the V. You could write that down yourself, or you could just copy it right now. So notice I put the mass over molar mass in place of N, because here's our N right here, nRT, and V is mass over density, so I plugged that in right there. Now, I'm going to isolate molar mass. You should be able to do this on your own. So pause your screen and get molar mass on the left side and solve for molar mass. And pause, because here it goes. You get this nice equation. Molar mass is dirt over P, DRT over P, because P is dirty, dirty. Just a mnemonic for memorizing the molar mass equation. Dirty over P, because P is dirty. And that's an equation for molar mass. Let's do a problem. Here's our information, and all we're going to do is plug this in. We're trying to find the molar mass. We'll just plug in our density, our gas constant, our temperature, our pressure, and recall that the gas constant, I gave it to you somewhere. Oh, I didn't give it to you. Ha! But we used it right here. Right there. The gas constant, in case you forgot it, is right here. 0.0821 atmospheres liters per mole Kelvin. You have to always make sure that your pressure units are in atmospheres so that they cancel properly, and your temperatures in Kelvin. All right, back to our problem. So now we know the value for R. That will be given to you. You do not have to memorize that, ever. So solve this problem on your own using the value for R. Notice let's see, we've got our density in grams per liter. Our temperature will have to get to Kelvin, and pressure is already in atmosphere, so we're good. There you go. 40.4 grams per mole. And I kept 3 sig figs because even though there's only 2 here, when I add 273 to this, our addition rules say I should keep the answer to the ones placeholder. So that becomes 3 sig figs right there. Okay, Dalton's law of partial pressures says that the total pressure exerted by a mixture of gases is the sum of the pressure of each individual gas. And we write this like this. The total pressure is P1 plus P2 plus P3 plus da-da-da-da-da, all the gases. P1, P2 are called the, do you remember the word for this? The partial pressure of gas 1 or 2. It's not that it's a fractional pressure, it's actually the complete pressure of component 1 or component 2, but it's only part of the total pressure, which is why we call it a partial pressure. There is also a variable called mole fraction. This is an important concept, mole fraction. It's the number of moles of a substance in a mixture. It's the ratio of the number of moles of a substance in a mixture to the total number of moles. And the symbol, it looks like an italic X. So mole fraction is your moles over the total moles. It's also equal to your partial pressure over the total pressure. So you can calculate partial pressure if you know mole fraction. If you know mole fraction and total pressure, you can calculate the partial pressure of any constituent whose mole fraction you know. Okay, and the concept of partial pressure is extremely important when we are collecting gases over water, because if you collect a gas over water, so there's a gas being produced here, it's coming up through this tube and then bubbling into this test tube that is open to the environment. The water's open to the environment. And the water will get pushed down the test tube as the gas fills up the test tube. The gas is going through the water, and as it does that, it pulls water vapor into itself. So this gas up here has the gas and the water vapor that it pulled with it. Now the water vapor pressure is dependent only on temperature. So in any problem, you will always be given the vapor pressure of water at whatever temperature the experiment is being done. So the total pressure in here, P total, will equal P gas plus P water. And if the level at the top right here is equal to the level of the water here, then you know the pressure of the gas is equal to the outside pressure. Right now it's not, because the test tube is showing the liquid level a little higher. When we do experiments, we move this test tube up and down up until the level of water in the tube is equal to the level of water outside the tube. That equilibrates the pressures so that P inside here is equal to P atmosphere. And then the gas would be the atmospheric pressure minus the water vapor. Okay. So here's a problem. We're going to collect this gas over water, and we're collecting oxygen gas. We want to find the mass of potassium chlorate that reacted. We're given the total pressure, that includes the water, and we're given the water vapor pressure at this temperature. So we're going to have to subtract off the water vapor pressure. So our first step is to subtract the water vapor pressure from the total pressure to get just the oxygen. So the oxygen is the total minus the water, 744 millimeters mercury. Whoops. Our next step, we need to use PV equals nRT to solve for moles of oxygen. We've got our pressure of just the oxygen. We've got our temperature, temperature, and we have our volume. So that's easy, we can get moles. Very important though, millimeters mercury you need to convert into atmospheres. So it's 760 millimeters mercury to 1 atmosphere. And I'm about to show you the solution, but you should write out your own solution for getting the moles. And I always teach you should isolate the variable and then plug in all of the numbers. So here's my pressure right here. This is the conversion to atmospheres. The volume. Here's my R again, and here's my temperature. And we got our moles of oxygen, and now we asked for, what did we ask for? Mass of KClO3. Well, if I have moles O2, I can go moles to moles and moles to grams. You again should do this on your own. Here's the answer, and there you have it.